Good morning or afternoon, depending on where you are. Welcome to the second round of the Grid Resilience at PNNL webinar series, which began last fall. I'm Stephanie Waldoff. I'm a senior researcher, a research scientist here at Pacific Northwest National Laboratories Joint Global Change Research Institute. Today is the second webinar and first deep dive of our Grid Operations, Decarbonization, Environmental and Energy Equity Platform, or GODEEEP webinar series. These deep dives will provide more detail on the science behind the capabilities presented 2 weeks ago in our overview webinar, along with information on how to access and use our tools and data sets. Today's deep dive will focus on our methods used to generate electricity load projections, which can be used to evaluate grid reliability and resilience. Our speakers will share results from scenarios of deep decarbonization and climate change. We'll have a brief Q&A at the end of each of our presenters' talks and a longer Q&A at the end of the presentation. You're welcome to type your questions into chat at any time, and we'll also be able to unmute you if you raise your hand at the end. And now I'm delighted to introduce our 3 speakers for today, Casey Burleson, Yang Oh, and Malini Gosal. Dr. Burleson is an earth scientist at PNNL's Atmospheric Science and Global Change Division, where he's worked since 2014. He has a BS in meteorology and a PhD in atmospheric sciences from North Carolina State University and an MS in applied physics from Columbia University. A meteorologist by training, Casey works on a broad range of topics, including simulating climate impacts on energy systems. He led the development of the TEL model, which you'll be hearing about today. He's also an advocate for open science, which is critically important for tackling today's most pressing scientific challenges. Casey is the PI for MSD Live, a collaborative open source platform for the multi-sector dynamics community at DOE. Dr. Yang Oh is an earth scientist at PNNL's Joint Global Change Research Institute and an assistant research scholar in the University of Maryland. Yang obtained his PhD in environmental science and engineering from the University of North Carolina at Chapel Hill and an MS in mechanical engineering from Carnegie Mellon University. Yang's research spans across energy system modeling, greenhouse gas mitigation, air pollution control, and climate policy analysis from global to subnational scales. Yang is also a contributor to the Global Change Analysis Model, or GCAM, and its submodules such as GCAM USA and GCAM China. Dr. Malini Gosal came to Pacific Northwest National Laboratory in 2018 as a postdoctorate research associate and now works as a power systems research engineer. Prior to joining PNNL, she finished her PhD from Texas Tech University in 2017. At PNNL, she works on solving various challenges of making the electricity grid cleaner, for example, planning under high renewable energy and grid impact studies for transportation electrification. Dr. Gosal has been the principal investigator for projects related to electric vehicles and electric grid related studies. She's the recipient of the Federal Laboratory Consortium Award for Technology Transfer for her contribution on Central American Grids Flexibility Assessment. And now I will turn it over to Casey.
Thanks, Stephanie. And welcome everyone to our first deep dive on electricity load modeling. As Stephanie said, my name is Casey Burleson and I'm a research scientist at PNNL. I'm a meteorologist by training, and for the last several years, I've been studying how climate change and extreme weather can impact energy systems. Today's webinar will cover how we produce hourly load projections that are responsive to climate change and decarbonization trends. But first, I want to take a step back and give a brief overview of the GODEEEP initiative in case you were unable to attend our kickoff webinar 2 weeks ago. I'll note that the kickoff webinar was recorded, and that recording is available on PNNL's Grid Resilience website. GODEEEP, or the Grid Operations, Decarbonization, Environmental and Energy Equity Platform, is a $4 million internal investment to bring together lab experts in power systems, climate, economics, and social sciences to study the issue of decarbonization. What's unique about GODEEEP is that we're looking at pathways to achieve a clean grid, but doing so using multiple lenses, including the resilience and reliability of the grid and the equity of the future energy system. For example, we're studying how decarbonization may impact disadvantaged communities. This holistic approach can only succeed by leveraging the full range of expertise available to us at the lab. You can see on this slide that the project is made up of atmospheric scientists like myself, hydrologists, electrical engineers, social scientists, and a range of other disciplines. Next slide, please. We do this work using a series of detailed numerical models that translate step by step large-scale forcing signals like decarbonization policies and climate change into hourly time series of wind and solar power generation and electricity demand. We then take those time series and run them through the nodal grid view production cost model to evaluate how the grid of the future performs when stressed by weather events such as heat waves and energy droughts. The final step is then to look at the energy and environmental justice implications of that future system. Next slide, please. In today's webinar, we'll be talking in detail about the electricity demand modeling that we do. As many of you know, long-term electricity demand projections are challenging for several reasons, including non-stationarity in the weather and climate signal, rapidly changing technologies, and uncertainty in the pace of adoption of things like electrified transportation. We address these challenges using a novel workflow that couples multiple best-in-class models that address specific aspects of the problem. Our electricity demand workflow is based on 3 unique models that we've built at PNNL. My colleague Yang O will talk about the GCAM model. I will cover the TEL model, and then finally we'll pass to Malini to talk about a very cool transportation electricity demand model that we built for this project. Next slide, please. As was covered in the kickoff webinar, everything that we do in GODEEEP is motivated by actual use cases that you all are grappling with right now. Some of the specific use cases that will be covered in this talk include projecting electricity supply and demand for system reliability studies, exploring load profile shifts with electrified transportation, and creating a baseline whole system projection that can be used to understand the potential impact of new transmission corridors. The final thing I want to convey is that not only are we doing all this important and interesting work, but we're also actively working to share it in near real time with stakeholders and communities like yourselves. We're engaging with partners in the energy system through these webinars and our website to share the results of our analyses along with the data and models that we're producing. We appreciate you taking the time to participate and engage with us in this process. And with that, I'm going to turn it over to Yang to get us started by walking through how we use the GCAM USA model in GODEEEP.
Thank you, Casey. So before we dive into all this exciting user case, I'm just going to provide a little bit more background and basically answer the question like why we need to use GCAM USA. So GCAM stands for Global Change Analysis Model. It's a global long-term integrated assessment model. So here we're using a version of this with better representation of the US at state level embedded within the global framework. So we call this GCAM USA. So broadly, GCAM's role is providing this kind of high-level boundary conditions of these long-term transitions towards net zero, such as the overall energy demand and the fuel mix across different sectors and states. And then with these high-level projections, like for every 5 years and for each state, our different use case and subsequent tools then can further downscale these results and dive into those operational details, so that we can better understand the system reliability and resilience at the utility scale. But the question is still like, why we need GCAM USA in particular? Can we just use a capacity expansion model or like extrapolation of historical data? The answer is no, because here in GODEEEP, we are very interested in understanding the implication of the net zero, i.e. Achieving net zero greenhouse gas emissions by 2050, as laid out by this US long-term strategy report. So from many literature, we already know that achieving net zero entails the system-wide deep decarbonization, such as this chart showing. So basically, this is an all-sector problem, not just the power sector problem. And future electricity load will be sensitive to many factors, such as the demand, climate impacts, the world economy, and the fuel prices. So that means we really need a holistic understanding of both the power generation and the demand, as well as this co-evolution of different demand sectors. And GCAM is exactly the tool we need to model such dynamics. So it endogenize such cross-sector linkages, such as energy flow or different energy prices, and even broadly like food prices, water and land that can be highly relevant to the sustainability related issues. And one thing I really want to highlight is that here we talk about net zero is not just CO2, it's all greenhouse gases. So there are other greenhouse gases like methane and F gases from all different sources and different sectors. And GCAM has the ability to track all of them. So in fact, the GCAM is a model to support this kind of long-term strategy report. So a few more details about GCAM US's multi-sector linkage. Overall, the economy will drive all the energy system dynamics here. And here we are using the socioeconomic pathway number 2, middle of the road assumptions, so SSP2. So this scale economy will then drive the overall system activities starting from the energy sector. And as you can see, we start from all the resource production, energy supply, transformation, demand, and go to all these kind of energy markets. On the other hand, GCAM has a very detailed agriculture and land use module tracking this supply and demand of all these agriculture commodities, even including like the bioenergy. So similarly, there are going to be agriculture markets that's going to track all these activities here. And GCAM will actually link all of them together to capture some of the very important dynamics, such as the competition between bioenergy and electricity. And for all these kind of activities, there's going to be like byproducts of those emissions from all those processes and water usages. And this could be a constraint in many cases when we dive into deeper results. And finally, all these emissions, especially greenhouse gas emissions, will fit into this simple climate model that we built together with the GCAM. It's called Hector, so that we can know the global picture. Remember that GCAM is a global model, so we will know that for a given scenario, whether it's going to hit 2 degrees or 1.5 degrees as this Paris Agreement laid out. Getting into more details in the energy sector, especially the power sector, we focused today. So you can see GCAM tracks different fuels and energy sources into this power sector, and all these go into the power generation module and go to electricity market. And then GCAM has a very detailed demand sector module. So all these building, industrial, and transport sectors, they will consume the electricity. Remember that GCAM is not just the power sector model, it has all the energies together. So at each steps at the top, like the resource production, transformation, end use, and this thing, at each step, all the technologies will competing with each other. So even in a net zero case, that fossil fuel seems less important, electricity is still going to compete with bioenergy and hydrogen there. So even we're focused on power sector today, our projection need to really consider those like competitors here. So zooming into the power sector, there's going to be a lot of details that we cannot cover all of them, but just here highlighting a few key points here. So overall, the power supply will be broken into these 4 load segments, try to capture this variation in the load curve. So that GCAM USA might consider the fact that some technology is more likely to be invested in the base load, such as nuclear, versus gas turbine will be more likely in the peak demand. And GCAM power sector uses a nested structure to represent the generation and technologies like competing at different levels, starting with the high level fuel level computation, down to each fuel might have different specific technologies. And finally, for each technology, it might have different cooling technologies there. So in terms of producing these realistic projections, GCAM also consider existing rules, such as those announced the coal retirement schedule and state-specific nuclear restrictions. And finally, GCAM also consider electricity trade across states within the grid regions and also between grids. So nationally, the total electricity will be balanced for the total supply and the demand, but the state could be either like net exporter or net importers. So finally, let's start to look at some results that GCAM USA produced. Here I'm presenting the co-evolution of the electricity generation and supply for 2 scenarios here. The BAU stands for business euro, which includes in current policies. And then we have an additional net zero case. Additionally, in addition to the current policy, we further consider the national goals of achieving net zero GHG by 2050 and also the clean grid by 2035 targets. And as you can see, the red line on the right-hand side, net zero implies much higher electricity generation compared to BAU. And this is really driven by the increased electrification rate across all these end-use sectors. Diving into the generation portfolio, here I'm showing the installed capacity by fuel for the entire VAC grid regions. VAC states total. So in the near term, you can see the overall magnitude is similar between BAU and NetZero, but the portfolio is really different. So this is really driven by the fact that we need to get clean grid by 2035. So you cannot have those conventional gas. For a longer term, you see a much bigger difference in terms of the overall scale. That's driven by the overall system-wide electrification. So that means after you decarbonize the power sector, now you need to move to all those detailed sector there. Zoom into the state level details. Here's the cumulative capacity investment for each VAC states. So besides the central NetZero case, here I'm additionally showing 3 alternative pathways looking at alternative assumptions about CCS, land use carbon emission management, or the demand side response here. So qualitatively, they have similar patterns, but nevertheless, you can see some minor difference there. So I guess this is another reason that we need to use GCAM to do this kind of scenario-based analysis, that we might not able to find the most the optimal solution. But more importantly, we want to understand these trade-offs so that we can be more confident about what's the robust findings versus what's the source of the key uncertainties. And finally, let's move to the demand side. Here I'm showing the sectorial electrification rate across different sectors. So overall, it's a system-wide electrification. Even the building sector already has a very high electrification rate. Nevertheless, you can still see higher electrification. It's keep going in this NetZero case. And for some other sectors with a lot of hard-to-abate sources, when you get to NetZero, you can see all the fossil fuel is phasing out, and higher electrification is going on here. And we will hear more details about these different consumers in our subsequent use cases and other deep dive talks. So with this, I'd like to transfer the mic to Stephanie and Casey.
Thanks, Yang. And so I think we can pause for any questions for Yang's section. We'll be able to obviously ask questions at the end to Yang as well. So please either raise your hand or put your questions in the chat. And I want to start with a question we have on whether you've considered the policies from the Inflation Reduction Act in your decarbonization pathways that you ran in GCAM.
Yeah, that's a great question, and that's in progress. It's not showing these data results, but we are already working on this and have this IRA representing the next round of the scenarios. So one nice thing about GCAM is that it's a state level, it has detailed energy sector, so it can really capture all these IRA provisions in the power sector, transport, and all the other details there.
Okay. All right, if we don't have any hands raised or more questions in the chat, let's move on to Casey.
Sure. Thanks, Stephanie and Yang. So as I said in the introduction, one of the goals of GODEEEP is to take these high-level signals such as climate change and decarbonization policies and actually translate them down into power grid operations. So Yang sort of covered how we capture those macro signals using the GCAM USA model, but to actually go down to power grid operations, we need to go down a further resolution, both in space and time. So the fundamental question that we're trying to answer is, how do we generate future hourly load profiles that are at a spatial resolution adequate for input to a UCED model, but that also maintain conceptual and quantitative consistency with GCAM USA's annual state level results? Next slide, please. And so the tool that we're using to do that is a model that we built at PNNL called TEL, or the Total Electricity Loads Model. So what TEL does is actually projects the evolution of hourly electricity demand in response to changes in weather and climate. So TEL is a machine learning based model, which is trained on historical loads and meteorology. And then we use those models to project into the future. The output of the model is projections of hourly electricity demand at the county, state, and balancing authority scale that are conceptually and quantitatively consistent with each other. And TEL has actually been released as an extensively documented open source code base. So if you're interested in the model, I encourage you to go to our GitHub repository where you can find out how it works. The animation that I'm showing here is the animation that's playing here is an example of a heat wave impacting the system in 2019. So you can see temperatures ebbing and flowing there across counties in the Western US. And then you see the corresponding electricity demand in select cities spaced around the Western US. While the example that we're showing here is for the West, TEL operates as a CONUS-wide model. So we're simulating all the balancing authorities in the CONUS. Next slide, please. In terms of how the model actually works, it's a step-by-step process. So as I said, we start by formulating these machine learning models that relate historical observed meteorology to the hourly time series of electricity demand for each of the BAs that report their loads in the EIA 930 dataset. Next bullet, please. We then use those machine learning models to predict historical or future hourly loads for each balancing authority based on a climate projection dataset that I'll talk about. Once we have these projections, we take the hourly load for each BA and distribute it to the counties that BA operates in. And then we aggregate those county level hourly loads from all BAs into annual state level loads. Using those annual state level loads, we calculate scaling factors that force our bottom up state level total loads from TEL to match the annual state level non-transportation loads from GCAM USA. And I'll note that in GODEEEP, we're separating out the transportation and non-transportation loads, and Melanie will talk about how we're simulating transportation loads. Once we have those scaling factors, we then apply them to each of the county level time series for that state. And then the final step is to output the results, which is a yearly 8760 time series of total non-transportation load at the state, county, and BA scale. And all of those different scales are conceptually and quantitatively consistent with each other and consistent with what's coming out of GCAM USA. Next slide, please. So in terms of data for the TEL machine learning models, you can see in the table here the predictive variables that we're considering. These are fairly standard weather variables that are go into most load models. We're also factoring in things like day of the week and hour of the day, and we account for holidays because the load profile changes. What we're actually trying to predict, our target variable, is the BA hourly demand from the EIA 930 dataset. Each of the machine learning models was trained on data from 2016 to 2018, and we did extensive evaluation using 2019 historical loads to evaluate the models. We won't go into the evaluation results, but I'm happy to say that the models perform quite well. And in terms of details, like each balancing authority is trained and evaluated independently, and we're using a hyperparameter tuning using a grid search approach. Next slide, please. So let me take a step back and talk about the climate projection data set that we're using. This is a unique data set that was developed using DOE Office of Science funding, and it's meant to capture the impact of climate change on the continental United States. So we start with historic data. So we start with 40 years of historical meteorology that reproduces the observed sequence of past events. So I'm showing two plots in the left here. The top is the annual mean temperature in CAISO balancing authority, and then the bottom is the annual maximum temperature in CAISO. And while these are annual values here, the data itself is hourly. So for each of these years, we have 8760 hours of all the different meteorology variables. So you can see some interannual variability in there, including particularly hot years such as 2006. So then we actually take this base 40-year sequence and we repeat it twice into the future. So if you go to the next slide, you'll see the first repeat of that. And in that repeat, we're applying additional gradual warming to the boundary conditions of the model. And that warming level is coming from a set of global climate models. So the four different curves here, the different lines reflect different RCPs, which are climate scenarios, and whether or not we're using climate models that are cooler or hotter than the multi-model mean. So what's really unique, though, is that we maintain that sequence of past events. So we can look at that hot year that occurred in 2006, and it will repeat in 2046 in our data set with that additional warming gradually applied. And if you advance one more slide, you'll see the second repeat of that, where you see a lot more divergence across the different climate scenarios. And again, you have that same event reappearing. So what that allows us to do is to look at historical events in the past that we know stress the grid and evaluate how they may play out in the future. So the base data set for this is hourly 12-kilometer data across the entire United States. There's 25 hourly meteorological variables, or 25 meteorological variables that we output every hour. And every 3 hours, we output over 250 variables. To create these temperature projections by balancing authority, we first spatially average that into counties and then population weight the counties to create annual 8760-hour meteorology time series for 54 BAs across the US. And that contains 40 years of historical data and 80 years of future data. And if you're interested in that data set, there's a link there. It's publicly available and we encourage you to reuse it. Next slide, please. So what we do in TEL is we take that climate forcing and the annual state level results from GCAM USA and produce these projections of load for different balancing authorities. So I'm showing one result here for Los Angeles Department of Water and Power in the year 2035. So the top panel just shows the temperature variations, and you can see heat waves and cold snaps in there, as well as the annual variability in temperature. And then the bottom is the actual load projections that are coming out of the TEL model. And it's kind of hard to tell in this plot, but there's two different colored lines down there. The blue is the business as usual, and green is our net zero scenario. And as Yang showed, in 2035, they don't actually diverge that much. But if you advance one more slide, we'll show the data for 2050. And now you can see a distinct separation between the two, with much higher electricity demand in the net zero scenario compared to the business as usual scenario. I'll also point out you can see distinct heat waves in the summer impacting the system and the corresponding load response to that. So if you look at the two plots on the bottom, they may look like they're the same. They have the same hour-to-hour variability. But if you zoom in on a given week, and if you go to the next slide, we'll show diurnal variability during the peak week of the year. You can actually see that they have different demand profiles for the business as usual and net zero scenarios. And I think this is really fascinating. So the big signals here are one, an increase in overnight loads in the net zero scenario, and that comes from charging transportation that Malini will talk about. And then you also see higher electricity demand in the mornings associated with that transportation signal there. And we think that this has really important implications for how you would design and operate the system. So for example, if you were heavily reliant on batteries, in the past, you may be able to charge those batteries in the early morning hours once the sun comes up and solar comes online. But in a high transportation scenario, like our net zero scenario, you're going to have higher electricity demand in the morning, and you may not be able to charge your batteries fuller. And that would have implications for how you would meet the peak demand in the later of the afternoon. Okay, the final thing I want to cover is how we do stochasticity or uncertainty in this. So in this example that I'm showing here, we're using a single deterministic weather year. So 2050 is just the 2050 weather year. And if you go to the next slide, you'll see we can run that through our model and evaluate the peak demand both in magnitude and in the timing. And in the 2035, this is showing data for CAISO balancing authority in 2035. Using the 2035 weather year, that single weather year, the peak load would be about 64,000 megawatts, and that would occur in early August. But we actually think that the weather could be treated as a stochastic or uncertain variable, meaning that any of our weather years could occur at any point in the future. And we can actually evaluate the impact of that by running multiple weather years to the model. So if you'll advance one more time, now you'll see what happens when we run 40 unique weather years through the TEL model and produce the 2035 loads. So these data points, there's 40 of them, have different weather years, but they all sum to the same total annual energy consumption due to how we're scaling with the GCAM USA state level projections, which are chronological. But the different weather years to give you different timings, different peaks, both in magnitude and in timing. And we think this is critical because a lot of the stress cases that you guys are trying to design want to look at specific aspects of stress. So for example, if you animate one more time, if you wanted to look at your system resilience in periods with low hydro, you could select weather years with late season peaks. For example, September peaks, which is when traditional hydro would be at a minimum. And if you advance one more time, you could also select weather years with extreme load peaks, just for testing overall system resilience to extreme loads. So we think this is a really unique feature of the model that we're excited to push out there. Okay, I think that's all I have for TEL, and I'm happy to stop and take a few questions now.
Thanks, Casey. We do have a few questions. There is one that has 4 parts related, so I'm going to go ahead and do that one. We'll take this now, and then others we can take in the longer Q&A at the end. So the question says, can you please share your experience regarding training data for the following points? Is the training data available as open source data? How can these load models be applied to new sites, locations for which historic data is not available? How much past data is required to improve the predictions, and what techniques are used to deal with the missing data and outliers? And I know that's a lot, Casey, so if you want me to reread them one by one, I can do that.
Yeah, I can take a stab at that, and I can see it in the chat. So
Oh,
is the
right.
training data available? Yeah, yes, it is. So it's one of the reasons we built TEL was to be an entirely open source model, meaning we're not using any proprietary data. So the load data comes from the EIA 930 data set, which contains hourly loads by balancing authority. And then the meteorology data, we're actually using the historical reanalysis product from the climate data set that I showed. I will say that we retrained the models using the NL DAS reanalysis weather data, and it got basically the same performance, and all that data is available. The second question, how can the load models be applied to new sites or locations for which historic data is not available? It could be a bit challenging if you don't have data to retrain. We do think that, you know, if there were a European group out there that wanted to adapt the model, all you would have to do would, you do need the historical data to retrain in other areas, but the actual code itself is very flexible and extensible. So we think you should be able to do that. The third question, how much data is required for improved prediction? This is a really good question. So we trained on 3 years. We started building this model in 2021. And so there's more historical data available since we did the initial training. And we think it's probably worthwhile to retrain the model at some point, because the more historical data that you give it, the better your predictions are going to be. There is a sort of issue there of sort of slow load growth over time that you would have to account for if you trained on like a 10-year data set or something like that. And then the techniques used to deal with missing data, we use occasional interpolation, but the EIA 930 data set is quite robust, and they actually do internal interpolation for the loads. And then because we're using simulation data for the climate, there are no missing data points in there. So I think we probably should move on to Malini, but I see some other questions in the chat that I can try and
I'll save the other questions for the end, except for I do want to address one question that says, I'm hearing a lot about data and modeling, but not much on the equity component of the GODEEEP. Can you comment on the application of all this to the equity considerations? And I just want to note that that's going to be the topic of our 4th deep dive. And we will put up you can access the links to each of those on the grid on the webpage, which we can put into the chat as well. So yes, there's going to be a whole deep dive on that topic. So and now let's turn it back over to Malini.
Awesome. Thank you, Stephanie, for the introduction earlier, and thank you, Casey and Yang, for setting up the stage for my portion of the talk. Today, I'll be talking about how we develop the hourly load shift for electric transportation at balancing area levels, which is also climate forcing and informed by the multi-sector dynamics model, GCAM, which Yang presented on. But first, why did we even create a separate module to project transportation electric load outside of TEL? This is because if you go next, yeah, yes, it's because electrification of transportation is going to disrupt the historical load shift. As TEL is trained on the historical load shift, and transportation is not a major component of that data, we thought it's meaningful to create a separate module outside of TEL. So our work essentially starts from GCAM's projection of yearly energy use for each state for different subclasses of electric vehicles. And our work basically boils down to spatially and temporally downscaling the energy projected from the state level energy projected from GCAM to a balancing authority level, and eventually at nodal level for the entire Western interconnect, basically at the 8,670 hours of data points, so that the information could be used for meaningful long-term grid operation and planning studies. I'll also discuss about how you can access our data set and create your own data set from the scripts that we have shared. And next one, please. And also the next one, I think I covered. Yes. So this slide shows all the 15 sectors which are considered in GCAM pertaining to transportation. And next, please. I have highlighted the ones to be directly electrified, or some other ones which would come online in future years. If you go one more time and maybe a couple of more times. So we categorized all these subcategories by weight class, because all of them have a predominated business model. So they have very similar charging behavior that can be translated from a given trip information. And these are the aggregated subcategories we have considered and developed load shifts separately. These are for light duty vehicles, medium duty vehicles, heavy duty vehicles, and then again aviation, rail, and ship. Next slide, please. This slide shows our overall framework for generating transportation electric load. This is also available on our GitHub page. Every module is color-coded, indicating whether they are dataset, model, or a particular code. As you can see, for a given decarbonization pathway for a year and informed by climate, we get a certain output from GCAM USA. And we have written a script to extract all the relevant output from GCAM USA output files, and that goes into 3 different modules. One goes to the EVI Pro Lite, which is a tool trained on a lot of LDV trip information and charging behaviors developed by NREL, and basically creates a daily hourly load profile that we have stacked together to get the yearly load profile. We also developed a code for mid and heavy duty vehicles. For that, we have introduced a couple of scripts that you can see here. Similarly, for the rail, ship, and aviation load ship, we have taken a simplistic approach due to lack of load ship information coming from this newer technologies. So we have distributed the hourly load at the same energy, same load throughout each hour of the year, but their spatial downscaling is more nuanced that we'll cover later. Next one, please. This is a more detailed diagram, and I don't plan to go over it. You'll find it in our website, especially in almost to be submitted paper. But I wanted to highlight that our actual implementation is more nuanced. It also takes into account the megajoule energy consumed per each vehicle, kilometers traveled for each subcategories, and some other information. We also have to do like some adjustment of the local load shapes developed for the local times to UTC time scales, and several other adjustment we have to do. Next one. This slide summarizes our logic behind especially downscaling the energy coming out from GCAM. For example, for light duty vehicles, we have used county level vehicle registration data from recent years. So we looked how the EVs from the Western states are distributed among each counties, and that's the information and adoption rate we have used for spatial downscaling for LDVs. For medium and heavy duty vehicle, it's slightly different. It's weighted by the population of the BS contained within the cities contained within that BA, which also has a clean energy policy. This is because we believe for MDV and heavy duty vehicles, such cities would be the pioneer. And this is a method adopted from a previously PNNL-led study indicated below. And for rail aviation ship, we have used county level information from the Bureau of Transportation Statistics. Next slide, please. So here we briefly showcase some of the sensitivity analysis we did for LDV load ships, which pertains to our study. For example, the first one shows the difference between weekday versus weekend load ship. If we keep all the other parameters same, the one on the bottom shows also an important sensitivity to temperature. Our climate model informs this information in generating the load profile. As you can see, with either too high or too low temperature, the efficiency of charging and discharging becomes low, and thereby we need higher energy to probably travel the same miles during that particular day. The last one shown on the right is the most important one, which is the sensitivity to charging strategies. We have considered two main ones. The first one is immediate, basically no management of charging. And the other one is using managed charging, which is load leveling, where vehicle still starts charging as soon as it arrives at its base, but it charges at as low as possible of speed so that it still finishes charging before next day's trip starts. So it's informed by the trip information for each subclasses as well. And for we have used several combination of these two charging strategies. For example, for 2035, we assume that maybe 30% charging would be through managed charging, and by 2050, it would be even more, at least 70%. Next one, please. This one shows for the net zero scenario, the overall load shape combining all the subclasses. And the top one, as we can see, although the overall the power demand is low, it's hovering around 15 gigawatt, but the bottom one is much higher. But due to the predominance of more managed charging in 2050, we can see the load shifts are less peaky. This, by the way, shows for a given month the average daily profile, so that it's readable, not a bunch of zigzags for the entire year. Next one, please. This slide shows our results at a glance, where we compare the transportation load for each BA and also the overall Western interconnect with respect to the system load. The first metric, the blue one, is basically average transportation load to average system load. The second metric is basically transportation load during system peak. It shows peak penetration. And the third one shows transportation load to system load during transportation peak. So all these three matrices show how the impact of transportation electrification is different for different BAs. The peak penetration varies from 2.5 to as high as 56%, but on average for the entire Western interconnect, it hovers around 10 to 20%, depending on which year we are looking at. And there are some BAs we see it's quite high, for example, in LA adjacent areas, LDWP, and also IID. We believe that it's driven by the fact that these this area is also a pioneer in early adopter of EVs, also has a predominantly residential and moderate climate. So all this factor into resulting into such high peak penetration and high ratio. Next one, please. This finally shows our data set. You would be able to look at it at the provided link. You will find the time series data set for each BA and also at WEC level for all the following years from 2025 to 2050s for two climate scenarios, which we believe would be extremes like RCP 4.5 cooler and 8.5 hotter, and two decarbonization scenarios, one for business as usual and a net zero. Next, I think that's yes, that's the end of my slide. In summary, like we developed a high resolution, temperature sensitive hourly load shape for a range of charging strategies informing grid operation model. And I'll be happy to take any more questions you have.
Thanks, Malini. I'm going to start with a few questions for Malini, and then we'll move to the other questions that we have from the chat so far. So first, can you tell us what are some of the uncertainties associated with the transportation load data set?
Yes, that's a great question. So for using it for the grid operations studies, we had to generate a deterministic data set, but we do understand that there are like a lot of uncertainties associated with this data set, and we plan to deep dive into it later. But some of it could be, of course, the uncertainty around the projection of like future technology, for example, like if there is a sudden growth into, I know, something more disruptive, maybe everybody is not having car and they're going for a mobility as a service or MAS kind of situation, then their charging behavior will change. There is also uncertainty around the climate change and basically the weather and everything. So, and some other disruption in the battery technologies. So we are aware of all those uncertainties around our assumptions. But as for our study, we plan to do those some deep dives in our data set in future.
Okay. The next question is, what does your ZEV scenario for transportation look like?
Yes, I think it was covered by Yang at detail, but in 2050 for net zero scenario, it looks at around 50% electrification and from energy wise, and 50% through other clean sources of fuel. And for LDVs, when we converted this energy information into fleet size conversion, we were looking at around 89 to 91% of electrification in light duty vehicles.
Okay. I think the next question is for Casey. How does TEL incorporate the adoption of DERs in the future? Heat pumps, BTM batteries, PV, etc. These don't seem to be broken out in the training data.
Yeah, that's correct. So I think the approach would be somewhat analogous to how we're incorporating the transportation data. So I think you would need a detailed sectoral model to simulate those different systems. So Malini gave an overview of the detailed modeling that we're doing for transportation. And then we were able to take those transportation sectoral models and just add them on top of our 8760 load profiles that are coming out of TEL. So we opted to start with transportation because we think the dynamics in terms of the profiles are pretty interesting, but it could be extended to something like buildings in the future. So if you wanted to look at building electrification of heating, if you had a detailed building model, you could run an electrification simulation through that and get changes to the load profile due to electrification of things like heat pumps. It gets a little bit trickier because in the transportation data, the historical loads are basically 0. So we didn't actually have to account for that when we trained the TEL model. But for something like buildings, which account for a much higher proportion of the overall total load, I think you would have to also run a historical simulation using your building model and then subtract those from the EIA 930 total loads and retrain the models in TEL so that the buildings were sort of simulated independently of TEL. And that's something that we're interested in doing in the future, but it's not within scope for GODEEEP.
Okay. The next question is for Yang. You mentioned that GCAM is a multi-sector model. What are some of the other multi-sector implications for achieving net zero beyond the energy sector?
Yeah, thanks. Yeah, this is a really important point that that I don't have time to cover. So as you can see, multi-sector means water, land, this kind of thing. And I briefly mentioned this bioenergy, land use stuff. So other implication would be like water, land, computation. So if you have a scenarios that's really focused on bioenergy, you're going to have bioenergy competing with the food, crop, land. And for the power sector, if you have a scenario with a lot of like cooling technology needed, then you are going to compete the water use with other sectors. So all these kind of are like more like sustainability related issues that we hope to further explore building upon these scenarios.
Thanks, Yang. We do have several other questions, but I want to let people know they can continue putting questions either in the chat or go ahead and raise your hand and we can unmute you and you can ask your question. So I think this next one's for Casey as well. California is planning to introduce highly dynamic prices that are at least hourly and different every day. This should change timing of electricity, but not the total very much. Is that something to integrate with building simulation models or machine learning from future data on how dynamic prices affect load?
Yeah, I think this is really interesting, and not to repeat myself, but I think you would need a detailed sectoral model in order to be able to simulate those price impacts. So some of Malini's results that she showed with different charging strategies are sort of a gateway to get at that. You can imagine that price of electricity drives a charging strategy. And based on the transportation model, at least you can get drastically different outcomes depending on what charging strategy you use. So if you had price data or price projections in the future, and you had a detailed sectoral model that could account for price variability and the impact of price variability, I think that would be interesting to do. But again, it's probably out of scope for GODEEEP.
Okay, one more question on TEL. Can you explain more on how the TEL model differs from day ahead or short-term load forecasting models?
Yeah, I think it operates in fairly similar ways in that it's very sensitive to weather, right? So if you think about short-term load models, they're basically testing the weather sensitivity of the system. And if you have a weather forecast for the next few days or the next week, then you would convert that into a load forecast. Where I think it's different is in our integration with GCAM USA for the long-term aspects. So GCAM is capturing things like changes in population, changes in economics, changes in policies that are really important for driving electricity demand. And because we're scaling our results so that we get the same annual state level values as what GCAM is producing, we're capturing those signals in a way that like a short-term model just isn't. It's not seeing any of those forcing mechanisms.
And that actually brings us to a question for Yang on GCAM USA. Why do we need a global model to study this subnational question?
Yeah, that's really a great point. Yeah, so even we are doing this US, the world is linked together. So if US doing net zero, the rest of the world is doing nothing, then that's just an unrealistic case. But on the other hand, if the whole world is doing like the net zero, that means some of the key technologies might be competing, some of the key resources like critical mineral, this kind of thing will be demanded globally. So definitely the world is linked together. So even US problem, we need to understand the global implications. And on the other hand, from a like broader like community purpose, when we do this kind of net zero scenarios or deep mitigation, we want to understand the global big picture, like what's the temperature targets or temperature outcome we are hitting at, like 2 degree, 1.5 degree. So this kind of thing is really like the broader question people are asking. So we want to have this kind of global big picture there.
Okay. One more for Casey. The examples of TEL you showed were for future projections. Can it simulate historical loads as well?
Yeah, it can. And it relies on the GCAM USA historical annual state level loads as well. But we have, for a different project, we've used the model to do historical loads going back to 1980 through 2019. And those are all 8760 as well.
Great. And one last one for Casey. Can TEL work with weather data sets other than PNNL's climate forcing data?
Yeah, yes, it can, and we would be very interested if someone wanted to do that. So essentially the model, the weather forcing just comes in CSV files where you have to feed it time series of temperature and a few other different weather variables by balancing authority. So if you were able to get those from like a different climate data set or even a different weather data set and wanted to run those through the model, all you would have to do would be update the CSV files and then rerun the model. And it should be fairly straightforward, but to the best of my knowledge, no one's actually attempted that yet. But if you're interested in doing that, we'd be interested in talking to you.
Hey, I want to give it a minute for anyone to raise their hand if they have anything they'd like to ask directly or any other questions in the chat. And while we're waiting for that, I do want to note that we have 3 more upcoming deep dives. And Carly just posted the information for those upcoming webinars on the on our website, how to register for them, and you need to register for each one individually. The dates are on there, and we hope that you'll all be able to join those as well. And I don't see any other questions or any raised hands. So I want to thank you all for attending. We really appreciate your time. And I want to thank our panelists for the excellent presentations. Hope you all have a good day.
Thanks.
Thank you.